Hello and welcome to this lecture. So, we're going to continue our study of eigenvalues and eigenvectors, and I started the introduction saying that the diagonal matrices are very simple and a more general matrix can be made to look like a diagonal matrix using eigenvalues, eigenvectors. So, we're going to study that specific idea in these sets of lectures. So, diagonalizability and its applications. Okay. So, what are diagonalizable operators? An operator T is said to be diagonalizable if there is some basis. Okay. See, in an operator, both input basis, output basis are the same, right? So, that's how we study it. So, if there is some basis with respect to which the matrix of T becomes diagonal. Remember, we always think of the canonical basis as our basic definition, right? So, the canonical basis, you have a matrix, maybe it's not diagonal, but there could be another basis, right? Some other set of linearly independent vectors that as a basis under which the same matrix the same operator may suddenly become diagonal. Okay, so that is called diagonalizable. If there is some basis like this for which this operator will become diagonal, the matrix of this operator will become diagonal. If that happens, then that operator is said to be diagonalizable. Think about this very carefully, right? So, when I define an operator, traditionally we associate it with a canonical basis representation. It may be non-diagonal, okay, but then I go to another basis. With respect to that basis, I can find a new matrix, which represents the same operator, right? I'll give you specific examples of how to do all this later on, but that's the idea. So, with respect to some other basis, you may get a diagonal matrix. Okay, so that is the tricky piece of work here, which defines this. So, the operator remains the same. Its matrix with respect to maybe the canonical basis is not diagonal, but with respect to some other basis, maybe it becomes diagonal. Then we can live in that basis. Any basis is the same in some sense. We can live in that basis and have a diagonal matrix, which is very, very nice and easy to work with. Okay, so that's the idea. So let's see how to think of diagonalizable operators and how to compute their diagonal representation and all that. Okay, so here is the fundamental, very, very nice connection between diagonalizability and eigenvectors. An operator T is diagonalizable if and only if. So, this is the crucial connection. Okay, so directly relates eigenvectors, eigenvalues to the operator. Okay, operator's diagonalizability. So, you need a basis of eigenvectors. When the basis of eigenvectors is there for Fn of eigenvectors of T, then T becomes diagonalizable. So, basically we need n linearly independent eigenvectors for diagonalizability. Okay, so it's a very nice connection. We can do a very quick proof of this. Is actually easy proof. Let's say an eigenvector basis is v1 vn. Okay, each vi is an eigenvector. So T of vi is some lambda I times vi, right? So that's what happens when you have an eigenvector vi. And this is also a basis. What are the coordinates of T of vi with respect to the same basis v1 to vn? Okay, that is nothing but 0 0 0 0 0 lambda I in the ith position, right? So T of vi is only lambda I times vi. No other vi prime appears in T of vi. So T of vi coordinates is just 0 0 0 0 lambda I 0 0 0 0. So once you have this, right, we know that the basis representation of T with respect to the basis v1 to vn is basically T of v1, T of v2, T of vn, the coordinates of that in v1 to vn. Okay, the coordinates also are found with respect to the same basis. So that is nothing but lambda 1 appearing in the first entry, lambda 2 appearing in the second entry, so on till lambda n. This becomes a diagonal matrix. So that is the basic idea. So matrix of T with respect to v1 to vn is diagonal. Okay, so it's a very easy proof to see that if you have a basis of eigenvectors of T, then T is diagonalizable, and vice versa. Everything here is you can go back, can trace back. So if you have a diagonalizable if you have a diagonal matrix representation for T, go pick up that basis. Those will be eigenvectors with the eigenvalues appearing on the diagonal. Okay, both are one and the same. Okay, so this is the central idea. So now we are left with the problem of finding out how many linearly independent eigenvectors are there for an operator. Right? If you can find that out, you are done. Okay, so here is a very, very crucial property. We have seen this before in the context of R2. So now we will see in the more general case. Supposing you have any linear operator T, you have two eigenvectors, which of course are non-zero, with eigenvalue lambda 1, lambda 2, and lambda 1 and lambda 2 are not equal. Whenever you have lambda 1, lambda 2 not equal, the two eigenvectors corresponding to them are linearly independent. Right? linear independence of eigenvectors is important, we see that whenever lambda 1 and lambda 2 are not equal, v1 and v2 are linearly independent. Basically, eigenvectors of distinct eigenvalues are linearly independent. Okay, wonderful, wonderful result. The proof is actually very simple. The proof, I had given it before, it's exactly the same. So, you can just go through. Supposing you say this v1 and v2 are linearly dependent, right? Then I need to show a, b is 0, right? That shows that v1 and v2 are linearly independent. If a linear combination of v1 and v2 goes to 0, I have to show a is 0, b is 0. That's actually very easy. So, you just hit both sides with t, you will get a lambda 1 v1 plus b lambda 2 v2 is 0. And then this is also 0. So, you multiply both sides by, let us say, lambda 2 and subtract, then the b part will cancel, you just get a times lambda 2 minus lambda 1, v1 is 0. So, this means lambda 2 is lambda 1. Okay, lambda 2 is not equal to lambda 1, which means a has to be 0. Similarly, b will also be 0. So, you can easily show that if lambda 1 and lambda 2 are not the same, v1 and v2 are linearly independent. Powerful, right? So, now this extends to multiple things also. Supposing you have lambda 1, lambda 2, lambda 3 being 3 eigenvalues which are all different, and v1, v2, v3 are the corresponding eigenvectors, then v1, v2, v3 are linearly independent. The same proof, right? So, you write the same proof, you can keep cancelling until you get these kind of behavior. Okay, so that's the interesting property here. So, basically eigenvectors of distinct eigenvalues are linearly independent. Okay, so this is a very nice property to have. Okay, so now based on the previous idea, the distinct eigenvalues have linearly independent eigenvectors, we can come up with some simpler, slightly easier to check conditions for diagonalizability in terms of multiplicity, right? So, we had this algebraic multiplicity, geometric multiplicity for all eigenvectors, right? So, you can use that and simplify some of these conditions. Okay, supposing you have algebraic multiplicity of 1 each. So, basically T has n distinct eigenvalues. Okay, if all the eigenvalues of T, the n of them, if you do determinant a minus lambda I, you find the roots and you have n distinct roots, then it is automatically diagonalizable, because the eigenvectors corresponding to each of those guys will be linearly independent, and that's done. Okay, so it's very easy. So, if algebraic multiplicity is never more than 1, then the operator is diagonalizable. Okay, nice and simple fact. More generally, if algebraic multiplicity equals geometric multiplicity for every distinct eigenvector, okay, both need not be 1. But whenever algebraic multiplicity is 2, what should happen to geometric multiplicity? It should also be 2. If algebraic multiplicity is 3 or for an eigenvalue, geometric multiplicity should also be 3. Okay. So, as long as both are equal all the time, nowhere it becomes strictly less than, right? Then also the sum of geometric multiplicities is n, which means there are n linearly independent eigenvectors. Okay. So, once you have this, in this case also you have diagonalizability. So, the only way in which you will not have diagonalizability, if geometric multiplicity becomes strictly less than algebraic multiplicity for any eigenvalue, then that operator will not be diagonalizable. There will be no basis under which that will have a diagonal matrix representation. Okay, so it's a very nice and simple condition. We can use that condition and quickly settle diagonalizability for all these cases: 1, 2, 5 diagonalizable, 1, 2, 3, 4 diagonalizable, 1, 1, 1, right? You should check geometric multiplicity, it will just be 1. Okay, algebraic multiplicity is 3, no chance. So, this also is not diagonalizable. So, here you have 2 algebraic multiplicity, geometric multiplicity will only be 1. This one is diagonalizable. Okay, so this has got just 2, this has got algebraic multiplicity 2, okay, and geometric multiplicity will also be 2, right? You can check that. Okay, see where I got it from. Likewise, this guy will also be diagonalizable, 1, 1, 2, 3. Okay, these 2 and 3 are, you don't have to consider, but 1, 1 also, when you subtract it out, you will have rank 2 here. When you subtract 1, that means nullity is 2. So, geometric multiplicity is also 2 for this guy. So, you will get it. So, in general, whenever you have repetitions like this on the diagonal, and it's upper triangular, right? Upper triangular is very nice. Above that, you should all have zeros. Then you will have geometric multiplicity also working out correctly, or in the same row, you should have all zeros, so that geometric multiplicity works out. If you have non-zero guys here, it will just mess up the geometric multiplicity and you won't come. For instance, here geometric multiplicity of 1 is 2, right, because you will get 0 when you subtract 1, but for 2, right, these guys are non-zero, so you will end up getting only 1. So, this will not be diagonalizable. Okay, so diagonalizable guys are 7, 4, 1, 5. Okay, or none of the other guys are diagonalizable. Okay, 2, 3, 6 and 8 are not diagonalizable. Okay, So hopefully that gave you a very simple condition for diagonalizability. We saw how simple diagonal matrices are. We will see more examples as we go along, but this is a very useful result to know between multiplicity and diagonalizability. Thank you very much.